The purpose of this lab is to develop a computational model to understand the physics of circular motion and using black holes, planets, and stars as case studies. We will also better understand how Newton's second law is related to circular motion and analyze the relationships between gravitational force, position, and momentum. First, we must discuss physics concepts that are fundamental to this phenomenon. Newton's second law is crucial because it shows the relationship between net force and momentum, and subsequently velocity and position. In this case, it also relates to the fundamental circular motion concepts. We note that when an object is in circular motion, its speed of trajectory is given by the net force in the direction parallel to its instantaneous velocity, while its change in motion is given by the net force in the direction perpendicular to its instantaneous velocity. It's also important to know the formula for gravitational force. For part 1 of this lab, we have a star at some initial position orbiting a black hole at the origin. The star has initial velocity and a black hole is stationary. Since we have the star's mass, we technically have the star's initial momentum as well. In this phenomenon, the system is the star while the surroundings is the black hole. As a preview of the results, I found that the star orbits in elliptical motion with its final position being the same as its initial. Also, I was able to find the mass of the black hole, which was not initially given. For this lab, I assumed that F net equals gravitational force of the black hole because that's the only force acting on the star. It's important to note that we don't know if the star is in uniform circular motion or not, so we cannot assume F net equals F net perpendicular. Also, since we are measuring one orbit of the star, we can find F net at a lot of different points and take their average to get an accurate reading of the gravitational force due to the black hole, and therefore we can find its mass. For my glow script calculations, I first inputted the mass of the star and the delta t. Then I applied Newton's second law to get the velocity and position update formulas. I then applied Newton's second law combined with the circular motion to find F net perpendicular and F net parallel. Taking the average of the F nets gave me an average of the gravitational force due to the black hole, and I then calculated the mass of the black hole. The results show me that the star has an elliptical orbit and that the black hole has a mass of 8.5 times 10 to the 33 kilograms. As a brief analysis, I'll discuss the differences between F net and the rate of change of momentum. First, note that the rate of change of momentum and F net are technically equivalent because of Newton's second law. However, the rate of change of momentum might be better used in an observation experiment where you can measure weight and velocity, while F net would be better if you already knew the force of an object. For example, the gravitational force of objects close to the Earth is simply the mass times g. For part 2 of this lab, there's a black hole at the origin and the planet at some position with a ship launching from the planet. The ship has an initial velocity, which I will determine. The black hole is stationary, and the planet is in uniform circular motion. There are also gravitational forces acting on and from the black hole, the planet, and the ship. In this phenomenon, the system is the ship while the surroundings are the planet and the black hole. As a preview of the results, I found that the ship could avoid the planet and the black hole by having an initial speed that was greater than the planet on the same initial trajectory. I later realized that the ship could also escape by slightly altering the direction of the ship to in between the planet and the black hole. For this lab, I assumed that there were no other forces acting on the ship other than the black hole and the planet. Therefore, I found the net force on the ship by using the gravitational force due to the black hole and due to the planet. Also, gravitation force is a non-constant force, so I used the non-constant version of the position update formula. For my glow script calculations, I inputted the mass of the black hole found in part 1 of the lab. Then I calculated the gravitational forces acting on the ship and acting on the planet. I then applied Newton's second law for the velocity and position update formulas. By trial and error, I found the initial speed that the ship could launch with to avoid crashing into the planet or the black hole. My results showed that if I started the ship with an initial velocity that was the same direction of the planet's momentum but a greater speed, I could escape. I also found that I could escape by going to the left of the planet's orbit and passing between the planet and the black hole. In analysis of the second half of the lab, I'll discuss how I could make the ship orbit the black hole and not just escape crashing into it. These figures show how I was able to achieve an orbit by setting the ship's initial speed in the y direction equal to that of the planet, but offsetting the orbit in the x direction so that the ship forms a slightly elliptical orbit.